All right, welcome back to the next chapter, Chapter 5, Cognitive Control, Working Memory, Executive Function. What are all these terms all about? Well, that's what this is going to be all about here. So let's get this going. One of the things that we're going to do to start is compare these concepts of cognitive control and working memory to attention, and we're going to call it internal attention. So what are we talking about? A lot of the stuff when we covered attention in the previous chapter, we could think of as external attention because we're really focused on how people allocate their attentional effort, their spotlight of attention, and these other kinds of metaphors to external stimuli. Right? We talked about the vigilance paradigm and how people have to attend to a screen and do this for a long period of time. We've talked about how in a divided attention task, people have to attend to the different stimuli that are part of a task. I used the driving example repeatedly there. And in that situation, with driving, you have to attend to various external stimuli, such as, um, the mirrors and the lane maintenance task and the speed maintenance task, and so on and so forth. So, what does that have to do with internal attention? Well, first, let me just mention this note in reference to Wundt real quick before I move on. Wundt, when describing cognition, described the first stage as perception, in which we bring information in from the world. But then he described what happens is that all of this perceptual information comes together to create the current content of our experience as we are thinking right now, right? The current content of our consciousness. And he refers to this as the apperceptive mass, right? The sum total of all of our current cognition. And this act of converting perception into the apperceptive mass is called apperception. And we can sort of think of apperception as somewhat synonymous with the concept of attention, especially that attentional filter or attentional bottleneck that determines which things we actually end up thinking about. And then the apperceptive mass is that content of our current consciousness, right? So the act of attention is creating the apperceptive mass. So they're directly linked to each other. Now, the apperceptive mass is something that could be very much like short-term memory and or working memory as we use it in current research. And we're going to talk more about that at the very end of these notes here. Now, back to the concept of divided attention a little bit here. One of the things that we see that causes problems with divided attention is that as the task gets more and more difficult, as there are many more tasks to include, right? So we have the driving task is already difficult, right? One of the reasons that it's difficult is that we simply may have to remember to do all of the different things, right? So I'm maintaining my lane, I'm maintaining my speed, I am watching for hazards, I'm monitoring what's going on inside of the car. And to check each one of those things requires that I actually need to remember that those things are part of the task, right? Um, and then, of course, once we throw the cell phone business in and we talk about distracted driving, then that just becomes more things that I have to remember to track. And so we can sometimes think of as divided attention failures or multitasking failures as working memory failures. So that's going to be relevant as we get into this. But another way to think about it is to think about the demand level of the task, right? So we might say that distracted driving is particularly impactful because maybe the act of talking and having a conversation on the cell phone is very, very demanding. And in the previous notes, we did talk a little bit about things like the attentional resource theory and the idea of cognitive load. So we want to understand that just a little bit. So this would suggest then that when we are doing tasks that are very easy, we can do divided attention fairly well, right? We can multitask when, walking and chewing gum, right? This is the old adage that people say that sometimes, you're just so out of it that you can't even walk and chew gum at the same time. And this is meant to suggest that you don't have the cognitive resources available to even do something simple like that. But in reality, of course, those are tasks that are not particularly demanding, so you should be able to do both at the same time. But in other situations where the task gets more difficult, we need to understand uh, what is actually involved with this, right? What makes a task difficult? We're going to approach it maybe in this perspective here. We can talk about tasks as being either automatic or controlled. This is a way of describing how demanding they are. Walking and chewing gum should both mostly be automatic processes. And so an automatic process then is synonymous with something that's not very difficult, and in particular is well learned, right? So couple of breakdowns here in terms of this is like just a side-by-side comparison list between an automatic and a controlled process. Automatic processes are fast and controlled processes are slow. Now, we've talked a little bit already about parallel and serial processes before, so we can bring that in here, right? So talking about feature searches in attention research, those are parallel, right? Meaning you can search the entire screen and detect the presence or absence of features in parallel with each other. So that could be an automatic process, right? But a controlled process, like a conjunction search, is slower because perhaps it is serial. You have to do one thing and then another in series. This is just simply going to take more time. But another way to think about this is simply just the issue of what does it mean to say a controlled process is controlled? And this is where the term cognitive control becomes relevant here, right? Is that we're going to need to talk about some sort of internal agency that is engaging in effortful mental control, whereas an automatic process doesn't seem to require this kind of control. It just happens on its own. It's almost as if we don't have to think about it very much. But a controlled process requires some thinking, right? The second point here is mandatory versus voluntary or involuntary, voluntary. A good example of this one to me is just reading, right? So I put the words on the screen, and when you look at them, ideally you look at them and you just immediately read them. You don't have to sound it out or think about it. In contrast, if we had young children who were just learning how to read, looking at the screen, most of these words are too big for them. But if we just had the word cat on screen, right? CAT, then how that would be one where they could potentially read it, but they might still have to slowly sound it out. So we would say that that's a voluntary process. They don't immediately read the word cat, but rather they might recognize, oh, those are some letters. And now I'll try to sound it out. C makes a K sound, and so on and so forth. So that means that reading for them is still very controlled when you're a novice, 5 or 6 year old child learning how to read. But for us as expert readers, it should be more of a mandatory process, right? I can't not read the words when I see them, right? If the word cat was on screen, it would just be read automatically, involuntarily, right? All of this, again, of course, is consistent with the idea that a controlled process has a high cognitive load. By load, we just mean a high demand, right? So load is a metaphorical word here, right? So you think about um, if you have a pickup truck and you put a lot of stuff in the bed of the truck, that's a heavy load, right? So that means the engine has to do a lot of work to drive. If the bed is empty, that's a lighter load, so then there's less work involved. So you can think of it kind of like that, right? Um, and then, of course, the idea is that when the tasks are easy or automatic, like walking and chewing gum, sorry, I'm still messing with my motion sensor back here, right? Uh, then I'm dual tasking as I'm doing this, right? Um, the automatic processes are less affected by these kinds of secondary tasks because they're just kind of working without too much cognitive control. So what we're going to see here is that when it comes to this kind of divided attention, dual tasking, multitasking kind of situation, that um, the degree to which any task is impacted by others is going to be a function of how controlled is this task in the first place. And if it's not particularly a controlled task, something automatic, it won't show a lot of impairment because of those distractions. But obviously, a controlled task is. This is relevant even thinking about reading as an example, right? So you hopefully, as an experienced expert reader, can read in a relatively noisy environment when there's music and noise and things going on. Obviously, it's a little harder, but still, you should be able to do it. But if you imagine again a young child who is learning to read, they're probably going to be even much more strongly impacted by background noise and distraction while they're trying to slowly sound out the words that they're learning to read, right? By the way, before I go on, that kind of points to the idea of skill acquisition a little bit too, right? That when you're learning to read, it starts as a controlled process, but through repetition, through practice and getting better, it gradually becomes automated. And that's pretty important. It's a very critical reading skill when you're in first grade, second grade, and so forth. A lot of times, what teachers do is they check for your sight words, right? Sight words are words you can read without sounding them out. You just immediately read it, right? That's an actual direct measurement of the fact that some of those words have become automatic for you, right? That you just quickly and immediately, mandatorily read them. But if you have to slowly sound it out and struggle with it, then it shows that for some of those longer words, those might still be controlled. You don't recognize them immediately. And there are different grade level kind of milestones and markers for what kinds of words and should be sight words at certain grade levels, right? All important milestones for skill acquisition for reading there. Okay, now this idea though of distraction, right? Of things being hard to control, a task requiring some degree of control and inhibition, shows up in a couple of different tasks as well as all in these real world things. So I use the word inhibition here. We need to unpack this a little bit. So when I'm driving, studying, reading, whatever it is, and there's things going on in the background, those are distractions. They're task irrelevant, right? So as we learned when talking about attention, we need to inhibit distractors. And an inhibition is something that is uh, uh, a form of cognitive control, right? And so it's effortful in a way. And sometimes we also have to inhibit internal distractors, right? I need to maybe force myself to not think about other things, memories, and things that are on my mind while I'm trying to drive or study and so forth, right? So we can see the effect of inhibition in laboratory studies, though. So here's one very, very simple basic task called the stop signal task, right? So it's basically a reaction time task here. So you're looking at the screen, you see a green dot on the screen, you press a button. That's it, right? But in the inhibition version here, we have two. We have an early stop and a late stop trial. So what we have to realize here is that the reaction time to pressing the button when you see the green dot is probably, maybe half a second. Could be a little faster, right? But, let's say 400 to 500 milliseconds. So that's somewhere close to half a second. But what we're going to do is before you have a chance to press the button, right? So we have a little time interval here between the time the green dot appears and half a second goes by before you press this button. Let's go with that 500 milliseconds. So on an early stop trial, what we're going to do is we're going to show you the green target, and then in that 500 milliseconds that's passing before you press the button, let's say we get about a fifth of the way into that, which would be 100 milliseconds, right? And then I show the red dot that says stop, which is the signal to say, oh, don't actually press the button this time, right? So when the green dot appears and nothing happens, you press the button. But when the green dot appears and then the red dot appears, you have to stop yourself from pressing the button, right? So that's your stop signal. And that means you have to inhibit yourself, right? You've already made a decision, green dot's there, I'm going to press the button. But now, I see a red dot, so I'm going to inhibit that and back off, and I'm not going to press the button. And what we see is that when the red dot appears early in the reaction time, like only 100 milliseconds in out of the 500, people are successful at inhibiting that reaction. But if we wait a little while, now let's wait till 400 milliseconds, right? And when it occurs late in the trial, that's when people will fail to inhibit themselves, right? So what we're seeing here is that inhibition takes time. It requires a little bit of extra processing and cognitive control, and that's going to take time. And when that signal occurs early enough, it gives me the time to stop this button press act before it ever gets underway. But on the other hand, once it's much more fully underway and I'm getting almost to that point where I'm pressing the button, it becomes harder to inhibit because, again, it's going to take some time to process that inhibition information. Maybe a little bit of a clearer example of a inhibitory situation is the famous Stroop task. So here I have some Stroop-like stimuli, right? So we have the words, these are color words. And the list on top are the color words written in the congruent color. So the word red is in red ink and green is in green ink and so forth. But the list at the bottom, we have incongruent colors, right? So the word green is written in red ink. And what we do in this kind of task is we ask people to name the color, not read the word, but to name the color of the ink as fast as they can. And when it's congruent, they can do it pretty quickly. But when it's incongruent, this is when things are a mess, right? So let's take a little deeper look at this here. So one thing we want to do is we want a baseline. So the baseline is just how fast does it take you to name colors? And so we're going to use these boxes here. So row one, you're just going to say red, blue, green, yellow. Row two, yellow, red, blue, red. Row three is blue, yellow, red, green, right? So that's your job. Name the colors. Now, when we go to the list on the top right here, we're going to do the same thing. We're going to name the color, not read the word. But these are congruent. So saying red, blue, green, yellow, yellow, green, blue, red, green, red, yellow, blue, we do that pretty reasonably fast. But importantly, we probably do it a little bit faster than in the first case where it's just the boxes of colors, right? And so the idea is that the alignment of the words that we are reading, which remember, word reading is automatic and it's fast and it's mandatory, right? So when I see the word red, it's just going to be like, oh yeah, mandatory reading the word red. And it's probably even more automatic than just naming a box that's colored red, right? So that speeds us up. And so we're actually faster in the congruent condition compared to the baseline version. But now consider the incongruent one, the bottom right here. Now again, row one, I have to say green, yellow, red, blue. And then I have to say green, blue, red, yellow, and yellow, blue, red, green. It's hard, right? What has to happen here is that that automatic act of reading is intruding. It's going to happen. It's mandatory. And then I have to stop it. I was like, nope, don't do that. Don't read the word red. I have to name the fact that it's written in green. So, okay, say green, not red, right? So we're not saying all of that stuff to ourselves internally, but at some level, that kind of decision making has to happen, where I have to inhibit the the tendency to automatically read and name the color instead. So it's much more harder. So this is a classic case of inhibition, right? That task of reading has to be inhibited. That requires cognitive control, right? I have some internal controller that's going to say, stop that, right? Don't do that. I'm trying to do something else, right? And so that's a form of inhibition here. We have some other cases of inhibition. So in the assignment task, we have, once again, colorful dots appearing on screen, sort of like in the stop and go task there. But in this case, we got a blue one and a green one. And I also have a blue button and a green button, and they're on the left and right side. So we have a compatible condition. Sometimes a blue dot appears, sometimes a green dot appears, and I just have to press the appropriate button. But what happens is that the blue dot is always on the left side of the screen, the green dot is always on the right side of the screen, and meanwhile, the blue button is on my left hand and the green button is by my right hand. So all of this stuff aligns spatially very nicely, and my reaction time to either the blue or the green dot is pretty fast. But what if we switch them, right? I was going to try to say flip or switch, and I said swip or something, right? Speaking of interference. So in this case, now we're going to put the green dot on the left. We're going to put the red dot, or the blue dot on the right, but we're going to keep our buttons where they were. So now the green dot appearing on the left, what do I do? Am I supposed to press the button on the left? No, I'm supposed to press the button on the right because that's the green button. So it's a little harder to perform this response. And so sometimes, again, you might have that tendency to, oh, the dot was over on the left, so I should press the left button. No, I have to inhibit and perform the other response. And that becomes slower, right? So again, every time we see this kind of inhibition process that has to occur, there has to be some form of cognitive control that inserts itself to inhibit one response and therefore activate the other response. Something similar is happening now in our flanker task as well. So we have three conditions here. What are we looking at? We have, um, first, notice that look at the column labeled number 1 here. We got 6 different stimuli shown as being presented over time. And it's XX less than and then XX, right? But that's an arrow pointing left, is how you want to think of it in the center there. So your task is to ignore the X's and pay attention to the fact that the arrow is pointing to the left. And then on the second trial, it's also pointing to the left. But then as we go down to the third trial, it's pointing right and then left and then right and then left. And that's our 6 trials here. Technically, you have more than 6 trials when you do this study. And so you just have to ignore the X's, and you can have 2 buttons, right? One on your left hand, so when the arrow is pointing left, press that button. The other by your right hand, and when the arrow is pointing right, you press that button. Or you could press the arrow keys on your keyboard even, or anything like that as a way to respond to this target. So clearly, of course, the presence of distractors is going to maybe slow you down compared to if there were no distractors, although that's not shown here. But one effect we can see is in the middle column, column 2, the distractors are packed in a little closer. And we talked about visual crowding before, so we can see the effect happening here that the crowding of those distractors makes it a little harder to identify and recognize the orientation of that center arrow. So we're going to see some delayed reaction time in this case, right? We call this perceptual interference because of the visual crowding is causing the effect. But now let's look at the third case here. So we have crowding here, right? Our distractors are crowded in a little bit, like in column 2. But notice our distractors are not X's anymore. They are other arrows that are sometimes pointing in the same direction as our center arrow target, and that's the case in trials 4 and 6. But in the other cases, they're pointing in the other direction. So then they become incongruent and they become unhelpful, right? So when we see these kinds of incongruent trials appear, reaction times to them are really, really slow. And on the congruent trials, reaction times are a little faster, right? And they're even more slow compared to the crowded condition, right? So crowding alone doesn't explain this effect, but rather in these incongruent cases, it's the crowding plus the fact that a conflicting response has been activated, right? I'm seeing arrows pointing both directions, so I have to inhibit one so that I can select the correct answer. And this extra inhibition of the activated incorrect choice, that requires cognitive control, that slows us down. So again, it's increasing the task here, task difficulty a little bit. What do we got next here is another way to think about how performance is impacted by task demand. In this case, speed. This is a little relevant, perhaps, to that stop go task, right? Because in this case, what's happening is when you're performing a task too quickly, you don't have enough time to process all of the information that you need. And so going too quickly it kind of inhibits your ability to process the information that's maybe necessary for task performance. And this shows up in a famous demonstration of human performance now called the Fitts Law, one of the few laws we have in psychology. So what Fitts Law tells us is that what you see the task here, a person is maybe using their finger to just point at a circular target. And what we want to tell them in the study here that is, I want you to reach and tap your finger in the center of that target as fast as you can. But importantly, I want you to not miss, right? So it's possible, for example, that I could just shoot my hand across there and get somewhere close to the target, but I might miss it a lot. So the instruction is important that I want to emphasize speed, but I also want to emphasize accuracy. So I want you to go as fast as you can, but while still being accurate, right? Don't go so fast that you're not accurate anymore. But also importantly is don't go so slow that, of course, you're going to be accurate, but the fact that you're just going super slow doesn't necessarily tell me what I want to know, which is this critical cutoff point, which is what is the fastest that you can perform this task while still being accurate. And this is what we call the speed accuracy trade-off, right? It's this kind of a cutoff line between the fastest you can go, but still being able to process the information you need to make sure that your finger does land in the target. And if you go too fast, you're going to miss the target, and therefore you're going to see that kind of speed interference, of course. Right? We want to, and what we see from Fitt's law, though, is that this cutoff occurs very, very consistently as a function of two properties of the task. They are labeled in the top right here as A and W. So A is referred to here as movement amplitude. It's basically the distance your finger has to travel from wherever the starting point is to where that target circle is. And then W refers to the width of our target. W seems a weird way to describe a circle. We think diameter here. But in other versions of the study, they use rectangular targets. So talking about width is a little more kind of obvious there. But it's this ratio of A over W, or as more formulated a little more mathematically here, it's the base 2 logarithm of 2A over W. That determines what we call the index of difficulty. And those numbers are calculated here. So for a particular value of A and W, we can have an index of difficulty of 3. Or if we make the distance longer, as in the next case there, we have an index of 4. Or if we keep the distance the same but make the target smaller, then we also have an index of 4. So what this would predict is that if this ratio is really that important for determining the movement difficulty, and therefore the amount of kind of cognitive control required in ensuring that my hand reaches the target, then I would expect that the movement time to the two stimuli that both have the same index of 4 would be the same. And that is exactly what Pitts found in this original research. And this is the graph from that research down here at the bottom. So the index of difficulty, or ID, is on the x-axis here, and the movement times are on the y-axis. And what we see is that there can be several different stimuli configurations, different combinations of A's and W's that all have the same index of difficulty. And importantly, all of those data points cluster together real close, suggesting that yes, people in fact do, their movement time is constrained to conform to that index of difficulty value, and they all fall perfectly on a straight line. If we did a correlation on this, it's like over 0.95 or something crazy like that, which is the kind of things that's pretty rare to see in psychology, right? Having, accounting for such a high percentage of the variance of human performance here, which is why it's called Fitt's law, right? It's a lawful relationship between index of difficulty and the movement time, because there's no other variables that we really need to care about too much that haven't yet been included into this function, right? To say a couple more things here about cognitive control. What we have here is when we are engaged in cognitive control, we have to do certain things, right? So all of the things that I've talked about with the Stroop test and the flanker task and so forth requires conflict monitoring, right? This means that in the Stroop test, when I know that my task is to name the color, but I am also having to monitor what else is going on, such as my tendency to read the word, I have to detect that conflict, right? And when it's congruent, there is no conflict. So the monitoring load is actually very low, and then I can respond very quickly. But in the incongruent list, or in the incongruent flanker task, the conflict suddenly goes up, and now the extra conflict monitoring is involved. And that's where cognitive control becomes relevant here, is in that. And then, of course, there's also conflict resolution, which is that now that I have two conflicting responses, to say one word and to name it, and to say another word, to say I want to read the word red, but I'm supposed to name the color green that it's written in. And so those are two conflicting responses. And so now I have to inhibit one. So this is called conflict resolution, or a tendency to press one button or another, depending on what condition I'm in a flanker task or in the Simon task, right? Another thing that also is relevant here is about error detection. Sometimes when we are doing these kinds of tasks, we're not always 100% perfect all the time, right? So even though I'm trying to prevent myself from doing the wrong thing, I will sometimes make a mistake. And now what happens is that we have to detect and realize, oh, wow, yeah, that was the wrong thing that I just did. And we have a tendency to want to correct it a little bit, right? And so this actually increases our cognitive control a little bit because then after I have detected an error, this increases my awareness of the error and makes me kind of have a tendency to want to do something about that. And this actually increases my chances of making another mistake. And this is an old study from Rabbit and Rogers where this tendency to make mistakes in clusters is called error perseveration. And it just means that errors persevere for sequences, right? So imagine, for example, on a flanker task where I'm supposed to press the left button because that's what the arrow is doing, but something about those incongruent distractors tricked me and caused me to press the right button. Uh, then what's going to happen is that on the next trial, even regardless of what the next trial is, I'm going to have a tendency to try to press the left button. Why? Because the left button was supposed to be the correct answer on the trial I made a mistake, right? So I pressed the right button even though I should have pressed the left. And so when the next trial comes along, I'm just going to have a tendency to try to press that left button because I know that was the previous correct answer that I should have done. And so now my tendency to correct my mistake has persevered into the next trial, which increases the chances of that next trial being an error as well, right? I mean, but if we got lucky, maybe the next trial is an arrow pressing left, so my perseveration doesn't cause an error. But this is just going to be 50-50, right? Because that's how these go. So what happens then is that because of that error detection phase, my risk of making a second error after the first error is actually elevated a little bit. And now that I've made a second error, my chance of making an error on the next trial, a third error in a row, is actually higher now as well, right? And so what Rabbit and Rogers then show is that in these kinds of experiments where people have to perform these binary choices like press a button or not, or press this button or that button, and you got to do it quickly, that errors start to cluster together a little bit. That once a person makes one mistake, they're going to probably make several mistakes in a row before they manage to somehow extract themselves out of that loop of errors and get themselves reset. And now that whole process of resetting yourself out of those errors, there's probably a little extra explanation we need for that. But that's the idea as I'm showing here, though, is that on any trial, E is the error trial. The very next trial, E+1, is also likely to show an error as well. Okay, now what we need to do next is a much more of a convoluted little experiment called the psychological refractory period research. And I think it will be best if I stop this video here so that way we can take a little break here. And as you come back into this one, we'll be fresh and ready to go to understand the details of these so-called PRP studies. Okay, so I'm going to go ahead and stop the recording and we'll come back to the next video next time.